Hi everyone, so today I'm going to introduce my work about analytical inference for visual inspection uncertainty in the context of transportation infrastructure. In this study, I will present the context of the study, how I will review the state space model already presented in the previous video that serve as a foundation for my work, and I will explain two methods I use in order to infer the inspector uncertainty, and I will finish with two case studies. To begin with, the context of this study is structural health monitoring. So structural health monitoring is the fact of monitoring the safety and functionality of structures over time. So the idea is to ensure that a bridge or a building is performing well and that it will not be dangerous or hazardous for the users. In my case, I focused in transportation network and more precisely on bridges. So I have several bridges in my network. Each bridge is identified by its ID, B1, B2, B10, etc. And each bridge is composed of different elements. For instance, cable, beams, things like that. And same thing, each element is identified by its ID E1, E2, etc. In order to perform structural health monitoring, we use visual inspection data. Visual inspection data are on-site condition evaluation of an infrastructure over time. They are a general evaluation for any kind of damage. They do not focus on a specific damage like corrosion or things like that. And it's a non-destructive evaluation. So how visual inspection are performed? So here you have an example of concrete beam, and you can see that there is a crack on this beam. So a team of inspector and an inspector will come, look at this element and say, okay, so on this element I have a crack and 25 of the elements can be considered as in bad condition, where 25%, the rest of it, will be in good condition. Doing a calculation, we obtain a grade, like 70 out of 25 from 100. This is the condition scale, where 25 is the worst condition possible and 100 the best one. Each time you see a Y in this report, it will represent an observation performed at time t. This observation and evaluation is really sensitive of which inspector has done the inspection. It depends on the experience of the inspector, because if you take two different inspectors, they will not have the same grade at the end on the element. So it's really depending on the subjectivity of the inspector. Overall, our database, we will have different structures, as I told you. So in this graph, you can see all the years where the inspection have been performed, and in the x-axis, it will be the different structures. So for instance, for the second bridge, we have an inspection at 2017, but also different inspection at different years, over 10 years, for instance. But for the other structures, it will be on different years. So you can see that depending on the structures, we have different time between each inspection. So this inspection is a database, is a large inspection database. We have like 10,000 bridges, 250 inspectors, million of data points. And we can see also that we have limited data per element and per bridges, because for instance, bridge 2, we have only 4 data points over 10 years, which is very few. And for each time series, so for each element, so in this graph, it's a typical report for all the inspection performed on one element. So you have in the y-axis the years, x-axis is the condition of the element from 25 to 100. Each blue point represents one inspection that has been performed. So for instance, this inspection was performed in 2010, and the inspector number 78 reported condition of 85 for this element. And you can see that there is only 4 points for 10 years of life of the element, so it's few, it's limited. And moreover, there is variability among the inspection data. Here, it seems like the condition is improving if you only look at the condition, where it should be degrading and going worse with time. This is due to the variability of the inspection data and the subjectivity of the inspection performance. There is existing model that allows modeling the degradation of an element. So using this data, which is the theme at the slide before, it is possible to model the degradation using a certain degradation model, but for this model, usually it partially quantifies the uncertainty of each spector, if they do. Meaning that there is a lot of degradation models that don't take into account the uncertainty of each inspector, and some of them only represented as an uncertainty, confidence interval, which is represented in red with the red whiskers here, and it allows modeling the degradation over time. But none of the existing degradation model take into account the biases of inspectors, and usually the uncertainty estimation is really time consuming. So now what we want to do is to estimate the bias associated with each inspector and reduce the computational time for estimating the inspector's uncertainty. Okay, so now I'm going to review the state-space model that I use as a foundation for my work. The state-space model have already been presented in this channel, and here I'm going to go quickly over it. So, using state-space model, we can model the degradation behavior using a kinematic model. So, for the kinematic model, we have an hidden state vector x, which is composed of the degradation condition, x dot is the degradation speed, and x dot dot the degradation acceleration. State space models are based on two models, a transition models that allows to go from time t-1 to time t, so you can predict the state at t when you know the state at t-1 using a transition matrix and a process error. And an observation model that allows modeling the observation made by an inspector, for instance, using an observation matrix and an observation error. The observation error is what models the uncertainty of the inspector. So here you can see that in this existing degradation model, the uncertainty associated with an inspector is modeled by a normal variable with a zero mean. These models are used in the Kalman filter algorithm to model the degradation over time. So, how does the Kalman filter algorithm works? It uses two steps. First, a transition step based on the transition model, which allows to predict from time t-1 to time t, and an update step that is based on the observation model and allows updating the knowledge of the hidden state vector at time t, looking at the observation at time t. So here you have the same graph as before with the years in the y-axis, the condition in the x-axis. I just crop here in order to see better what we are doing. So here we have an example of element where we have 3 inspection available, and we start our modelization, with a certain state. So here the red dot represents the prior knowledge about the condition in 2017. Using the transition step, we can forecast the next year what will be the condition in 2008. So the line here represents the estimate of the model, and the gray shaded area represents the confidence interval for this estimation. But in 2018, we have an observation available. So using this observation and the uncertainty that is associated with this observation, we can update the knowledge using the update step of our estimate. So you can see that we were overestimating compared to this observation, so we are correcting the observation, the estimate. Then we can do the same thing for the other years, so we can transition the state at the next year using the new states and to 2009. Here we don't have observation, so we use this estimate as the only estimate. And we do the same thing for the next year. We use a transition step to forecast. We have an observation this time, so we can update the state and use this new red dot as our estimate for 2010. Same thing for the next year. And afterwards, when you don't have any more observation to correct your estimates, you can only forecast over time as much as you want, but you can't update. So it's only forecasting using the transition step. In order to perform this Kalman filter algorithm, there is a few parameters that are needed. There are two kinds of parameters. The parameters are associated with the inspector uncertainty. So in this framework, the inspector uncertainty is modeled by a zero mean normal variable. So we only have the standard deviation associated with each inspectors. And all the other parameters that are, for example, the initial value for the states, some parameters to determine the way the transition model works, things like that. And for now, what was used is an optimization using maximum likelihood estimate, where the likelihood is obtained from the Kalman filter. So we optimized this vector theta using the maximum likelihood estimates, and it was done using the Newton-Raphson algorithm, which is a gradient-based optimization framework. The limitation of this work is that, as I told you, the observation error is a zero mean normal variable, which means that the inspector biases are neglected. And using Newton-Raphson algorithm is time consuming, especially with big data sets. And if we want to infer bias, it means increasing the number of parameters to estimate and increasing the computational time. Okay, so now I will introduce the methodology used to infer the inspector uncertainty, first using the revised gradient-based framework, then a new analytical framework. So first, why do we care about the bias? If you look at the inspection performed by an inspector, if you knew the true state of an element, which we don't in real case, but if we knew, there would be an error between the observation made by the inspector and the true state of the element. This graph will represent the error for every inspection performed by one inspector. So one inspector does an observation, there is an error. In real case, we can't quantify this error, but here it's just an illustrative example. If we consider an unbiased inspector, if we take all the observation he has performed, the error will be centered to zero. And the current model is modelizing this distribution by a normal variable centered to zero. However, if the inspector is actually biased, what will happen is that all his observation will be shifted, because having a bias means always over or underestimating the state of an element. For instance, an inspector that has bias +2 will always have a +2 on all these observations. So it will shift all his inspection from 0. If we're still using the current model with a 0 mean, what will happen is that the distribution will flatten in order to take into account the largest value, so the standard deviation will increase. We don't want that because it's not representative of what we have. So that's why we want to introduce the bias in the modelization in order to model this distribution by reparameterizing the distribution. So each time you see mu v, it represents the bias of an inspector ye. So the first way to infer this bias is to use the same gradient-based framework I introduced earlier. So this is the old gradient-based framework, and what I will do is just add the bias in the modelization and in the model parameters to be estimated. By fixing the bounds and things like that, we'll be able, using the same Newton-Raphson algorithm, to infer the biases. However, it will be time-consuming. So to replace this framework, I developed an analytical framework to infer these parameters within the state space model. To do that, I need 2 new normal variables. One for modeling the bias, so VB will be modelizing the bias with a normal variable with a mean and a standard deviation, and VS will be modelizing the standard deviations, which will be a 0 mean normal variable. These 2 new variables, VB and VS, are added to the eigenstate vector and will be inferred with the other parameters in the Kalman filter algorithm. However, in order to infer VS, the standard deviation, this is not enough. So we are able to infer the biases with the Kalman filter algorithm, but for VS we need an extra step. This step will be based on the approximate Gaussian variance inference method, which was developed in another work. I invite you to go and check the work in order to have a better idea of how this approximation works. And here I will just try to give you a hint, but not going too deep into the explanation because it will be too heavy for this presentation. So we have our normal variable Vs that we want to infer. It's represented by this distribution, a 0 mean and a standard deviation. What we want to infer is the standard deviation sigma s. If we look at the definition of the variance, we have the expected value of v squared minus the square of the expected value of v. As it's a 0 mean variable, we only have this term left. So now we need 2 new normal variables, one to modelize Vs squared, which will be approximate from Vs. So we have a new distribution modeling Vs squared, and we want also the expected value of Vs squared, so mu s squared, to be modelized as a normal variable. These 2 new normal variables will be used to update Vs. This one is used for the transition from time t to time t-1, and both of them are used to update the knowledge about the parameters. I did not present all the equation of the AGVI in this presentation, but I invite you to go check them. So now we have 3 steps to update our parameters. The transition step of the Kalman filter, update step of the Kalman filter, and update step of the AGVI. How do we use them with our framework? So we start the estimation process with broad parameters. So a 0 for the biases and certain parameters for the standard deviation, which is estimated using the gradient-based framework. So what will happen is that we'll process the data starting from one element. We are going to process yearly all this information. So for one element, we have different inspections. So we start at time, here it's 2005. We use the Kalman filter algorithm to go over this time series. And each time I see an observation, I will update the knowledge of these parameters, of the parameters associated with the inspector that is concerned by this observation. So with this first element, I will only update the parameter associated with inspector 5. Then I continue processing the data. Then I will only update the parameters associated with inspector 14. So at the end, after processing the first element, I have only updated 4 parameters. The bias and standard deviation for the 5, and bias and standard deviation for inspector 14. Then we go to the second element, and we do the same thing, using this as prior value for these parameters. But all the other parameters are not updated yet, because we didn't have observation that are associated with these parameters. So we continue to process the data element by element, year by year, and we do that until the end of the database. So all this process is one epoch, and we do that over several epochs until we have convergence. In order to verify and validate the methodologies, we use 2 case studies. First, a synthetic case studies, then a real case studies. For the synthetic database, we generated 18,000 time series that look like this. So we have, as before, the years on the y-axis, condition in the x-axis, remember, from 25 to 100, just cropped here in order to see better what is happening. So for this time series, I generated using the Kalman filter transition step only. I generated a true condition, 250 inspectors, and randomly using the inspectors to make observation on the true condition. So these observations are made from this true condition using the uncertainty of each inspector. So the blue points are the inspection, and each inspectors are associated with a bias between -4 to 4 and a standard deviation between 0 and 6. The standard deviation is represented by the whiskers, and the bias is represented with the blue asterisk. So the blue asterisk is actually the observation minus the bias. So if for instance, inspector 103 has a bias of +2, so his observation corrected by the bias is reparametrized +2. So using this time series, I infer the inspectors parameters, so the bias and standard deviation, using the gradient-based framework. In this graph, you can see the estimation for the bias using the gradient-based framework. So each blue dot represents one estimate. So in the x-axis, you have the true value of the parameters, which we know because we are in the synthetic case. And in the y-axis, you have the estimated value of the parameters. So each blue point represents the estimates for one inspector. So for instance, this one, the true value was something like 0.2, and the estimated is -0.1, -1. So obviously, a perfect estimation would be over this red diagonal, and you can see that we are close to it but not on it, and that there is a bit of variability in the estimated values, but it's still a really good estimation based on what we have as a database. We have the same thing for the standard deviation. So this is the estimation for the standard deviation, this is for the bias. If you want to compare the estimation with the previous framework with only the standard deviation without considering the bias, using the same database, this is what we obtain when using the gradient-based framework to estimate the variances while considering the biases as 0. So you can see that there is a tendency of overestimating the value for the standard deviation, which is associated with the fact that the standard deviation increase in order to compensate that we don't take into account the biases, as I showed you before with the distributions. So I use these two these two estimations, so without biases and with biases, in time series analysis in order to see the difference in the forecast on the forecast condition. So here you have an example of synthetic database, synthetic inspections data for one element. So here's on the y-axis, condition in the x-axis. The blue points are the inspection available for this element. So first, without biases, I retrieved the standard deviation of the inspectors, and I could model the estimated condition for this element. So in red here, you have the estimated condition for the element. The gray area is the confidence interval for 1 and 2 sigmas. The black dashed line you can see here is the true state of this element. So you can see that there is an error in the prediction, of course. Now the same thing while taking into account the biases. While taking into account the biases, so you can see that here I represented the correction with the biases. So using this new available data, you can see that this time we are really closer to the real state. So in blue it's the previous estimation, in red is the new estimation. So you can see that while taking into account the bias, we are closer to the real state than while not taking into account the bias. So this is one example, and I did that with all the time series I had for the validation set, for the testing set. After 10 years of prediction, I look at the error between the true state and the estimated state. And these graphs represent the average error for all the time series available. So in red, it's the average error for the model while taking into account the biases. Black dashed line without taking into account the biases. So you can see here it's for the condition estimate, here for the speed estimate. Then you can see that in both cases there is a real improvement in the forecast condition, that the error is smaller while taking into account the biases. Now I did exactly the same study with the analytical framework. So first, here I represented an estimation of I follow the estimation and the evolution of the knowledge of a parameter using the analytical framework. So here it's for the biases. In blue, here the blue line represents the estimate of the estimated value of the parameters. In the y-axis, you have the number of inspections that has been processed for this inspector. X-axis, the value of the parameter. So Each time we see a new observation, we update the knowledge of the parameters and we move on this graph. So the blue shaded area is the confidence interval for 1 and 2 sigmas, and here in red dashed line is the true value of the parameters. So you can see that the estimated value of the bias is converging to the true state, and that the uncertainty around this estimate is decreasing. Same thing for the variance. So you can see that obviously we have a good convergence to the real parameters. So this is for one parameter. If we look at all the parameters, you have this graph. So it's exactly the same graph as before. Each point represents one estimate. One inspector is a parameter estimate. So the true value in the y-axis, estimated value in the x-axis. And you can see that we are a bit farther away for the bias and for the standard deviation to the true state compared with the gradient-based estimate. And we have also more variability among the parameter estimates, but it's still a good estimation. We are really close to the true state, and it is considered to be a good estimation. Using the average forecast error I presented earlier, I did exactly the same comparison as before. So in red you have the analytical framework parameters, the forecast error using the parameter estimated using the analytical framework, and in black dashed line the same error using the parameter estimated by the gradient-based framework. So you can see that this time the gradient-based framework is still has better performance than the analytical one, but it's really close. Now we can move on to the real database. So the real database is composed only of the structural category beams, meaning that for all the bridge I only look at the beams of each bridge in order to reduce the database. So this database is composed of 19,000 elements, 275 inspectors. For this database, we don't have the true state available. So we need to have something in order to compare our estimate with. So what I did is take all the last observation of each element, each bridge, and removed it from the training data. So these last inspection are not available and not used for the training, and I only used them as idle inspection to compare after the estimations of the parameter, to compare the predictions on the condition. Using the gradient-based framework, I estimated the parameters. So we have the biases here, standard deviation here, so you can see the histogram for this estimation. And to compare with, this histogram is using the gradient-based framework, but without considering the biases. So you can see that once more, if you look at the second beam, there is a tendency to have bigger standard deviation if you don't consider the biases, which indicate that it is likely that there is a bias in our inspection data. Same thing with the analytical inference. We estimated the observation, and you can see that here there is a bit of an error. It's not completely centered to 0, but still it's acceptable estimations. Here is an example of time series analysis in the real case. So it's exactly the same as before, but this time it's real data. Without biases, we have an estimated standard deviations for each inspector, and here it's the estimated state while not considering biases. This red dot is the idle inspection that wasn't used for the training of the data. So I only use it here in order to compare the estimated state to the idle observation. So you can see that there is still a gap between the estimated and the observation. And when I consider biases, here I'm getting closer to this observation. So in dashed here, you have the estimated state without biases, red with biases. So you see that we are getting closer to our observation. This is not enough in order to compare the framework, it's only one example. In order to have a metric to compare the different framework, we use log likelihood for the test set. And so for the gradient-based framework without biases, I had -3.7, with biases -3.6, and with the analytical framework -3.62. So you can see that the gradient-based framework with biases is still the best out of the three, and the analytical compared to the gradient with biases is really are close, even if the gradient-based framework is better. So using the analytical framework means losing a bit of accuracy on the estimated state values of the parameters. However, if we look at the computational time in order to estimate the parameters, using the gradient-based framework, estimating all the parameters was 75 hours while considering the biases. Out of these 75 hours, 33 hours were used for the inspector's uncertainty only. The 42 hours left are for all the other parameters, like initial values, things like that. And using the analytical framework, we still have the 42 hours, but the 33 hours were reduced to 20 minutes. So the computational gain in this case is significant. In order to do these studies, we have several hypotheses. First, the inspectors are globally unbiased, meaning that on average, all the inspectors, the mean of all the inspector biases is 0. The biases and standard deviation over time are stationary, so there is no improvement possible for the inspectors. And the bias and standard deviation are independent from each other. So in the future work, what could be interesting to do is to introduce a non-stationary bias and standard deviation in order to allow the inspector to improve over time, which is normally the case, and to introduce and to reduce the computational time even more by changing the estimation process for the remaining parameters. In conclusion, the bias inference works using either the gradient-based framework or the analytical one, and it improves the estimation of the degradation model. There is a real improvement in the computational time using the analytical framework. Even though the accuracy is a bit less than for the gradient-based framework, the improvements compensate for this lack of accuracy. So that's it for the analytical inference of the inspector uncertainty.